Hi and welcome to Broke Abhiyantrics. So we are going to solve some problems on the stress and strain. So we are going to learn about the properties of materials while solving these problems. Alright, so anyway, let us not dilly daddle and we'll start with the problems. Uh, a prismatic bar with rectangular cross section of 20 mm cross 40 mm, length 2.8 meter is subjected to an axial tensile force of 70 kilonewton. The measured elongation of the bar is 1.2 millimeter. Calculate the tensile stress strain in the bar. So quietly straightforward. Uh, we just have to apply the basic formulas, which are the stress is equal to pressure or the tensile force divided by the cross sectional area. So here we're going to have 70 into 10 to the power 3 whole divided by the cross sectional area is going to be 20 into 40. So let us keep the units in Newton per millimeter square itself. If required, we are going to convert that to the pascals, else we are going to stick on to the Newton per millimeter. So 70 into 10 to the power of 3, so we are going to get something as, so in the denominator is going to be 800, in numerator 80 divided by 800 is going to be around 70 divided by 800 into 1000. So we're going to get somewhere as 87.5 Newton per millimeter square. So they also have asked us to calculate the strain in the bar. The strain is going to be the change in length divided by the original length. So this is our engineering strain, so this is our engineering stress. So uh, so the change in length, they have given it as 1.2 millimeter and the original length is somewhere around 2.8. This is in meter, so we'll have to convert that into millimeter. So we're going to have 1.2 divided by 2.8, so it's going to be around 4.2 into 10 to the power of minus 3. So note that. So in the strain we are not going to have any new units. So in stress we are going to have Newton per millimeter square or pascals. Pascals is nothing but Newton per meter square. So usually this value is going to be so huge that we are going to use megapascal or gigapascals. So megapascal is going to be 10 to the power of 6 and gigapascal is going to be 10 to the power of 9. So, and also we are going to, let us also cover about something called as actual stress, so, and actual strain. So what is these things? So note that, so if we have a material and we apply some tensile stress for this, so this is going to deform, right? So while we are applying stress, the area or cross sectional area of this guy is going to be continuously decreased, right? So if we are taking into account of that particular change in the area, so we are going to call the particular stress at a particular point of time as the actual stress. So for example, so the actual stress is going to be something called as the load applied, so divided by the actual area at that particular instance of time. So similarly for the actual strain, so we are going to call it as epsilon a, so that is going to be the change of length, so divided by the length at that particular instant of time. Okay, coming to the second question, so we're going to have uh, a bar of length 5 meter is made of a structural steel having the stress strain diagram as shown in the figure. The yield stress of the steel is 250 megapascal and slope of the linear part of the stress strain curve, which is the modulus of elasticity, is 200 gigapascals. So let me just write it down. So the yield stress that they have given is 250 megapascal and the modulus of elasticity is nothing, is given as 200 gigapascal. All right, so the bar is loaded initially until it elongates 7.5 mm. So the delta L is going to be 7.5 millimeter, and then the load is removed. How does the final length of the bar compare with the original length? All right, so now since they have said that the bar is loaded and the load is removed, so let me just assume that the bar is loaded until the elastic or the yield point and then the load has been removed. Since the yield point will be always greater than the elastic point, So whatever, if the material is loaded up to the yield point, it is not going to come back. I mean, it is not going to trace back the initial length. So let me assume that this is going to be the loading point, and after it reaches the yield point, without any increase in the stress, the strain on the material keep on increases. That is the graph that they have given. So here what happens, the strain continuously increases without any increase in the stress on the material. So after some point, so what are we doing? We are unloading this particular curve. So we are unloading this back. So now, technically speaking, so this particular curve had to reach this point. It has to be something like this, but it is not reaching point 0. So we have some extra residual energy or residual strain. So this body has been deformed. So to find out the original, or let's say the final length of the bar, we are going to have to find out the length for this particular strain. So easy way of calculating this is, so we are going to have to find out the strain at this point. Let me call this as point A, and also have to calculate the strain on this point B. If I subtract this, I'm going to have this particular strain or the residual strain. So I can easily calculate the change in length for this particular residual strain now. So let me just easily calculate the strain at particular point A, which is the elastic point. Uh, let me just call it as epsilon A is nothing but stress. I'll be just using the simple formula, which is the modulus of elasticity is equal to stress divided by strain at any given point. So according to this, at point A, so I'm gonna have that is epsilon A is nothing but sigma y, that is yield stress, divided by the modulus of elasticity, which is nothing but the yield stress is 250 MPa. So I'm going to convert this 200 GPa to MPa, that is nothing but 2 into 10 to the power of 5 gigapascals. Sorry, this is megapascals now. I've just converted this. So megapascal and megapascal is going to cancel out. So I'm going to have 250 divided by 2, 1, 2, 3, 4, 5, 0. So I'm going to have 1.0.00125 is the strain. So at point B, so again I'm going to do the same thing. The strain at point B is equal to, again the stress is same, since there is no excessive loading that is happening, the stress is going to remain the same. But here, so we're going to have, or instead of using this formula, I can go with the change of length divided by the original length formula. So the change of length, they have given it as 7.5 mm, and the original length is given as 5 meter. So that is nothing but 5 into 10 to the power of 3 millimeter. So millimeter and millimeter is going to get cancelled out. So I'm going to remain with 7.5 divided by 5000. So it will be around 0.0015. Right. So here, next, the elastic recovery, whatever that have been recovered. So it is nothing but this guy. So this is going to be the recovery from here to here. This is recovery. So let me calculate the recovery now. So elastic recovery is equal to sigma y divided by E. So that is nothing but, we have already done that, 0.00125. So the permanent or the residual strain is going to be equal to epsilon at point B minus epsilon recovery. That is nothing but point B minus point A. So as simple as that. So we are going to have 0.0015 minus 0.00125. So it is nothing but 0.00025. So now the permanent deformation is going to be, let me call it as delta L permanent. So that is going to be epsilon. See, let me call this particular point the returning point as point C. Now epsilon at point C minus, or sorry, into L. So this is nothing but epsilon at point C is just now we have calculated this 0.00025 into the length, that is nothing but 5 into 10 to the power of 3. Let me just keep it in millimeters so that I can tell the final changes in the millimeter itself. So this is going to be 1.25 millimeter. Now I don't know whether it is longer or shorter, so I'll have to go back to the question. So they have told that initial length part until it elongates. So in the question they have mentioned it as elongate, so this is going to be 1.25 mm longer than the original part. If they have given the stress strain curve for compression load, so this was going to be the shorter one. Okay, so moving on to the next question, we have to match the following materials to their respective properties that is given here. So let me just start with the first one, which is elastic material. So in the elastic material, the stress strain curve is going to look something like this. So I'm going to write this for tensile curve. So this is going to be the yield point. So before that we are going to have the elastic limit. Sorry, this is going to be the elastic limit and the yield point. So this is going to be the point of proportionality. So until this point the stress will be directly proportional to strain. After this, not much. And after this we are going to have the plastic region. So meaning that after this, whatever the material will have some permanent deformation. So at the topmost point we are going to have the ultimate stress. So at this particular point is a point of failure. So right, so with this particular knowledge we are going to have to look into the options. It does not store energy, obviously. So if the elastic material has been loaded beyond the point of yield or beyond the point of elasticity, it is going to hold some energy, right? Whatever that we call it as a residual energy. So this point option is no ruled out for the first option. Has no plastic region in the stress strain curve. Obviously this is also wrong. Beyond the point of elasticity, whatever the curve transverse, meaning this point, is going to be the plastic region. Behaves as a spring, not quite much, right? So obviously if the material, if it is in plastic region, it is not going to act as a spring. Offers resistance to deformation. Every material does that. It's not so much special for, let's say, elasticity. Let us come to the fifth option and then let's come back to the fourth one. Does not offer resistance to the deformation. Obviously we do have some stress given. The stress is nothing but resistance to deformation. So here we do have stress here. Comparing with all the 5 options, the option 4 is going to be much better suit for this elastic property. So let me just write it down. For A, it is going to be the number 1. Sorry, for A, it is going to be the number 4, this guy, right? And let me take the second one, which is the rigid material. So for a rigid material, again, let me just draw a stress strain curve for a rigid material. So it is going to look something like this. So if we have this, so if it is a strain, if it is stress, so the rigid material will have stress strain curve something like this, meaning that there is going for ideal rigid body, so there is not, it doesn't deform basically, right? So whatever it only takes up the stress, there is not going to be any strain because there won't be any deformation, meaning the delta L is going to be 0 for an ideal rigid body, right? So keeping this into account, let me just go with all the options, right? So it does not store energy, obviously, right? So whatever, if there is any strain, then it stores energy, then the material will store the energy. If the strain itself is 0, then the residual energy is going to be 0, or even if the body is loaded, so if the strain is 0, it doesn't hold any energy. So the first option itself is the best suit, so we are going to write B1. So let me come back to the options. The option C is ruled out and option 4 is also ruled out. So option 1 and 2, A and B is still remaining. Let me just take the next material, which is going to be the plastic material. So for plastic material, again, just let me just draw a stress strain curve. let me just draw a stress strain curve for a perfectly plastic material. For a perfectly plastic, the stress strain curve is going to be a horizontal line, meaning that without any changes or increase in the stress, the strain continuously changes, right? So for constant stress, the strain continuously increases. It is going to be the material property of a plastic. So uh, let me just come back to the options. Does not store energy, it is going to be false. We have already utilized this. Has no plastic region in the stress strain curve. All of this is a plastic region, meaning that if there is going to be a deformation, it doesn't come back to its initial position, right? So again, this option is also ruled out. Behaves as a spring. No, it doesn't, because it will permanently deform. Offers resistance to deformation. This has been already been used. Does not offer resistance to deformation. Exactly, right? So if even without any changes in the stress, so the strain continuously increases, meaning that it doesn't offer any resistance to the deformation. We are going to have C as 5. And again, for both first option and the second option, both of these are same. We'll have to inevitably go to the last material, which is a resilient material, right? So for a resilient material, so let me just quickly talk about what is resilience. So resilience is nothing but, so if we have a stress strain curve something like this, right? uh, let me just take the particular curve. So while it is loaded, so the energy or the strain will be something around here at this particular point, and assuming this point is within the elastic limit, while unloading, the material will travel back to its initial position and will reach 0, right? So here at this particular point, this total area under this curve is what we call as resilience, meaning that the material or the volume of the material that we are going to have stores up this much amount of energy while it is under stress, and while unloading, it is going to give out all of this extra energy for a resilience material. So we are going to look at the different options. Option 1 is ruled out, and option 4 is again ruled out, and option 5 is also ruled out. So has no plastic region in stress strain curve. Obviously, if it goes beyond the elastic limit, we are going to have the plastic region here. So here in this particular resilience material, this will store the energy, and while unloading, it will give out the energy. Obviously, this is going to behave as a spring. So for option D, the third one, we are going to use. So there is something called as a high, is going to be something called as high tension steel, HTS. So this is a highly resilient material. So we are going to use this in making for springs and suspensions of an automobile. So high tension steels are used for this because of this particular property of resilience. It can take up energy, store that particular energy in the volume of the material, and while unloading, it gives out all the energy. Hence, it safeguards the chassis and the other components while doing so. So 4153 is the option 1. The option 1 would be the right answer. Right, so let me just move on to the next question. So we are going to have another theory question. A structure is said to be linearly elastic if load is directly proportional to the displacement, load is inversely proportional to the displacement, energy is directly proportional to the displacement, energy is directly proportional to the load. A structure is said to be linearly elastic. Elastic meaning if a member or a body is loaded, after unloading, it comes back to its initial position. That is nothing but an elastic property. Linearly elastic meaning stress strain curve would be linear. This only happens only if it is directly proportional to the displacement. If it is inversely proportional, we are going to have a parabola here, right? Again, going to the next question. This is going to be the last question in this particular video, which is not the characteristics of a fatigue failure, right? So fatigue failure, what do we have that as a fatigue failure? So in a particular stress strain diagram, let me just first explain what is fatigue, and then we'll go to solve this problem. We are going to have a particular point under the elastic limit, where we call as a endurance limit. Okay, so if a material or a body is loaded more than the endurance limit and less than the elastic limit, and while unloading it is going to store some amount of residual energy, and if a particular body is continuously unloaded and loaded and unloaded, this residual energy is continuously will be stored in the body until this residual energy will be so huge that it goes beyond the point of failure, and here the body is going to be failed, or let's say a rod is going to experience failure if the residual energy increases beyond the point of failure, right? So this accumulation of this residual energy is what we call as a fatigue. This usually happens if there is a dynamic load, or if the loading and unloading is done in a cyclic manner, right? So here what exactly happens? First, there's going to be a formation of crack. So this formation of crack is what we call as a initiation time, right? So the number of load cycles required to form this particular crack is what we call as initiation time. And next, what we have something called as propagation time, and propagation time is nothing but the number of load cycles which is required for this particular crack which has been formed to propagate throughout the cross section, and then finally the material is going to break out. So this is what we call as a propagation time, right? So after the propagation time, after the crack has completely traveled through the cross sectional area, the material is going to fail, or the block is going to break. So regarding this particular thing, we have a question here, which is not a characteristics of a fatigue failure, right? So this is the question that they have asked, which is not. So let me just go through the first option, rough fracture surface. In the fracture surface, there's going to be rough surfaces as well as smooth surfaces. So let me just keep the first option. The first option itself is going to be the right answer, but let me just see the other options as well. So what does the option 2 say? Option 2 says we are going to have rough and smooth areas on the fracture surface. Yes, we are going to have this. No plastic deformation, obviously, since if we are loading only under the elastic limit for the body, there won't be any plastic deformation whatsoever. So this is also correct. And conchoidal markings on a fracture failure, this is nothing but, let's say, some spherical kind of markings on the fracture surface. Obviously we also going to have this. So the only option which is left out is the option A. This, we don't have only rough surface on the fracture area, we are also going to have all of these as well, right? So let me just end the video here, and see you guys later. Take care.